So good evening, everyone, and I welcome you all to today's live session for the course Elements of Mechanical Vibration, NOC25-AE17. We are into the week 9 live session for the course, and we have already completed 8 live sessions up till now. And so this week, again, we will be discussing about multi-degree, actually two multi-degree of freedom system to be precise. But like in the last 2 weeks, we were discussing about 2 degree of freedom system. We were actually concentrating on a particular case of the multi-degree of freedom system. But this week we will be more focused upon multi-degree of freedom system and how do we work with those. Just a second. Now the recording is fine. Okay, so this week was all about how do we deal with multi-degree of freedom system and how do we find or write the equation of motion for a multi-degree of freedom system and how do we find the like he finally came to the conclusion that okay we can use a matrix form for writing the equation of motion and then how do we find out the elements of those matrices. We then learned it by using the other methods and everything. So okay, we'll start with the questions. So this is the first question wherein we have to derive the equation of motion of the system that is given below. And then we have to also find its inertia influence parameter. So we'll come to the influence parameter later. First, we'll work upon finding the equation of motion. Now, since we have already done a lot of work upon finding out the equation of motion for a single degree of freedom system, for a 2 degree of freedom system, and for a multiple degree of freedom system, and how for a multiple degree of freedom system we define the constraints on the basis of those constraints, how do we decide that how many degrees of freedom are present in the system? Because last week or maybe last to last week we discussed about the concept of degrees of freedom, and on the basis of degrees of freedom we actually decide that how many degrees of freedom a system is having and how many equations do we require in order to properly show that how my system is behaving, right? So for this system, as you can see, we have a 2 degree of freedom system. It can be seen very clearly. We have two things. We have a trailer which has a mass capital M, and then we have a compound pendulum which is actually tied on the trailer, and then it is free to oscillate. Okay, so we have a trailer first, something like this. I'll model it like a box, and it is on wheels, and then the surface is frictionless. There's nothing that is said about the friction, so definitely we'll consider the surface as frictionless. And we have two viscous dampers, so definitely we are having viscous damping over here. So now this is our trailer which has a mass capital M. So definitely the mass is going to be concentrated at the center. So it is going to have a gravitational weight which is capital M into G. Apart from that, we have two springs K1 and K2 that are attaching our trailer to the two supports that we have. So definitely these, now since we are assuming that a trailer is moving in the forward direction with X, X dot, X double dot, for now we'll just consider, yeah. And then there is a forcing as well, which is F of T. Although it is not mentioned that what kind of a forcing is there and whether it is sinusoidal, constant, anything, but we can just write it in terms of capital F. So because of this, now the springs are going to apply force over here as K2x and the dashpot K2x dot, K1x, C1x dot. Okay, now these are the forces that are acting on the mass. Now, if you look over here, we have two wheels on which the trailer is kept on the ground, correct? There are two wheels. Okay, there are two wheels that we can see over here. So we'll assume that there are two wheels only. Anyways, so now because of these two wheels, there is going to be reaction force like this. These are the two reaction forces, right? Now, what is the value of the reaction force? See, since the trailer is free to move in the horizontal direction, in the vertical direction, it is restricted, right? It cannot move in the vertical direction. Okay, it is restricted to move in only in the horizontal direction. So in the vertical direction, we are going to have a force balance between the total mass and the reaction forces. Now, as you can see that the mass is symmetric, so the reaction forces are going to be half of the total mass of the system, the total weight of the system. Okay, so the total weight is definitely this. So the reaction forces is going to be divided into two parts as by 2 and capital M plus small m into G by 2. These are the two reaction forces. Okay, I hope this is clear. Now, if I look into, there is a compound pendulum as well, right? Now that compound pendulum is also going to give some contribution into the movement of the system. How? Let me just show you. This is the compound pendulum, or I should draw it something like this. This is the compound pendulum. Okay, it is having a displacement of theta, a displacement of theta. Okay, and this theta is in the anticlockwise direction for now, we have assumed. Okay, now because of this movement theta, okay, because of this, and definitely it is going to have a mg over here like this. Okay, definitely it is going to have that. Now, yeah, like this. Now, if you look over here, yeah, if you look over the compound pendulum, what is actually happening? Let us make a better view of that over here. So, yeah, this one, this is theta. Firstly, it is having a mass which is located at the center of mass, which is mg. Okay. Secondly, we can just break this mg into two parts, right? One is going to have a contribution in the direction of the pendulum, and the other is going to be perpendicular. Anyways, apart from that, we have this mx double dot. Since this whole trailer is having a x double dot of acceleration in the forward direction, this compound pendulum is also going to have that much of acceleration in the forward direction, apart from having its own dynamics because of its frame of reference, which is moving, it is also going to have that acceleration. So small m into x double dot. Okay. Apart from that, we are going to have okay, a force in the perpendicular direction and then a force in the radial direction. This force in the perpendicular direction is nothing but m L by 2 theta dot square. Okay, and here this is going to have m L by 2 theta double dot to be precise. This is going to have a direction in over here because definitely theta double dot is directed towards that direction only. Okay, and this is not actually this, its component is going to be in this direction, but this, okay, just a second. This one is going to be theta. This is theta. So this is also going to be theta because then theta 90 minus theta and then theta. So it is going to have components in the vertical direction and the horizontal direction. So definitely its component in the horizontal direction is going to contribute towards the x movement. So we are going to have mx double dot plus plus m L by 2 theta double dot into cos theta, right? Into cos theta. And then this force is actually, the centripetal force. So it is directed towards the center over here. So this over here is going to have a component like this. Okay. If this is theta, this is nothing but 90 minus theta. Wait, I'll just make it over here. We have something like this, which is m L by 2 theta dot square. This is going to have a component in the horizontal direction. And since we know this angle is theta, this angle is going to be 90 minus theta. So its component in this direction is going to be nothing but minus m L by 2 theta dot square sine theta. Correct? This is something like m omega square into r, the force that is directed towards the center. And then it comes with a minus because we have 90 minus theta. In the opposite direction of x, we have the x in this direction. Okay, I hope this is clear. This was for x. Apart from that, we also have components of theta, right? So the first thing is that this point mass at the center of mass is going to have its own inertia, right? Apart from that, this rod is going to have own inertia, let us say, which is J. So it is going to have a inertia force something like J into theta double dot. Okay, and then we have for the mass as well. Okay, then we have ml by 2 theta double dot. Definitely we have the force and we have to just multiply it with the arm length, so we are going to get the torque. Apart from that, if we look closely, we have in the direction of theta, the sine theta component for mass. Mg is going to have a component in this direction, which is mg sine theta. Now this mg sine theta is going to cause a torque in the opposite direction of motion. Okay, and we have mx double dot as well, that is going to contribute. Now, if I want to find or write the equation of motion, firstly for x direction, what are the things that we have? Firstly, we have capital Mx double dot plus small mx double dot. Yeah, capital Mx double dot plus small mx double dot. Then we have k1x plus k2x plus c1x dot plus c2x dot. Right. Apart from that, we have forces because of the presence of the compound pendulum. Right. Like, look over here. First, this one. First one is this, and second one is this. We have to also add this in the x direction. So it is going to be plus m L theta double dot by 2 cos of theta minus m L by 2 theta dot square. This is going to be equal to f of t. F of t. Now we'll assume, or not now, first we'll write for the theta direction, then we can assume for linearity. For theta direction, what are the forces that we have? First is J into theta double dot. J is nothing but, for this kind of a rod which is pivoted at one end, the J is going to be ml square by 12. So we are going to have ml square by 12 into theta double dot plus we have m into theta. Look over here. We have this ml into theta double dot by 2, which is a force which is going to contribute in the theta direction as moment. It is going to be ml by 2 theta double dot into L by 2. Okay. Apart from that, we have mg sine theta. It is also going to contribute. So that is going to give us minus mg, not minus, it should be plus mgl sine theta by 2. Okay. Apart from that, again, we have this. We have this mx double dot. This is also a force, but then this is not in the perpendicular direction. So we can take its component in the perpendicular direction, and then that component is going to contribute towards a torque. So we have mx double dot, its component in the direction perpendicular, cos theta into L by 2 into L by 2, and then this is going to be equal to m of t, where m of t is nothing but some external torque, which is not specified in the question, but we have assumed that there is some external torque. So this is going to be the equation of motion in the theta direction. Now we have two equations. Since we had 2 degrees of freedom, x and theta, we have derived two equations of motion. But if you look closely, these equations are not linear. They are actually non-linear, right? But in this course, we are mostly concerned about linear equations. So if we consider that theta is very small, we can make this equation from non-linear to linear. So theta is very small So sine theta is nearly equal to theta. Cos theta is equals to 1. And then we have this thing over here. Yeah, this is fine. This is fine. Yeah, okay. So now if we replace these values, what is going to happen? Using the linearity assumptions, we get, so I'll add another slide. See, we are going to have m plus m into x double dot plus k1 plus k2 x, which was linear only, as you can see over here. This was linear, this was linear. So we can write it as it is. C1 plus C2 into x dot. Then we have ml theta double dot cos theta by 2. Cos theta is going to be 1. So ml theta double dot by 2. And this is going to be equal to f of t. This is the first equation, which is linear. For the second equation, which is in the direction of theta, what do we have? We have, sorry, ml square by 12 theta double dot. Then we have ml by 2 into l by 2, which is going to be ml square by 4. Okay, maybe we can just write it like ml square by 12 plus ml square by 4, which is going to be, okay, we can simply replace this with ml square by 3, adding the first two terms. Okay. Then again sine theta, for small theta, it is going to be equal to theta plus mgl theta by 2, and then we have this thing where cos theta is going to be 1. So m l by 2 x double dot is going to be m of t. So these are the two linearized equations. Now, if I want to write it in matrix form, what I can do is I can just separate x and theta. Like if I want to write it in terms of matrix, I just need to transform it in a form something like m into x. M is a matrix, x is a vector, x double dot. Then k, okay, k x c x vector dot is equals to f, which is again a vector. Something like this. This is how we write it, right? So if I want to write the given equation in this form, what will I do? I will just replace x vector as x theta. Okay. So my matrix M is going to be capital M plus small m, 0, 0, ml square by 3. No, but we have theta double dot components. It won't be 0. Okay, this is a coupled equation. We'll have ml by 2 over here also. So this is the mass matrix. Similarly, we are going to get the stiffness matrix as K as K1 plus K2, 0, because here we don't have any term of theta. Then again over here we do not have any term of x, so this is going to be 0 mgl by 2. Okay, I hope this is clear. Similarly for c, okay, just a second. Over here it should be a sine theta actually. This term we neglected. Why? Because we have theta dot square into sine theta, which is very small. Anyways, we can write the C matrix as C1 plus C2, 0, 0, 0, and F matrix as, sorry, vector, F is a vector, as F of t, M of t. So this is the way in which we write our multi-degree of freedom systems equation in a single equation by the use of the matrix. Okay. Now, you see, another part of the question was find the inertia influence coefficients. Now, firstly, what is inertia influence coefficients and why do we even require to find it out? See, this was a 2 degree of freedom system and it was simple to solve it. Correct? We have a 2 degree of freedom system and it was simple to just solve it because we had to deal with only two equations, right? We had only two equations that we had to find out, and they were not complicated at all. They were having simple terms. However, if my equation is difficult, my system is having 3 or 4 degrees of freedom, and then if I have to find out the equation of motion, it becomes difficult for us, right? It becomes difficult for us because it requires a lot of computation. And when we are into a lot of computation of our own, it may happen that we can do some small mistakes because of which there could be a large effect on the system. And then it is time consuming also because it's purely mathematical. And yeah, so what do we do is that, yeah. So then what do? We then try to find out influence coefficients. Influence coefficients are nothing but something that helps us to find these these matrices. These matrices. So you see over here what have we done? We have basically converted a multi-degree of freedom system into a single equation using the matrices, right? So if we already have the M matrix, K matrix, and C matrix, we don't need to even find out the equation of motion. We can just use the matrices, right? And write the equation of motion. So that is what this inertia influence coefficient works with. Now, inertia influence coefficients, as the name suggests, it is used to find out the inertia vector. Sir, bahar. It is used to find, I'm sorry. Uh, so it is used to find out the over here. It is used to find out the inertia matrix, which is nothing but this thing. The one associated with the mass or inertia, like for mass in case of the translation motion and inertia in case of the rotational motion. Okay. So now, if you look over here, I don't know anything about my system. Okay. I assume that my equation is very tough. I'm not able to find out the equation of motion, but I need to find out so that I can model it and I can know that what are the environmental conditions and what are the behavior that can be seen in my system and what are the things that I should avoid for the failure of my system for in order to definitely avoid the failure of my system. So this inertia influence coefficient is found out by the thing that it's like Mij. Okay, Mij. So Mij is essentially nothing but the momentum. It is the momentum that is required by the system. So it is basically the momentum at the point J, momentum at the point J, for which there is a unit change of the velocity of the system at point I. Unit change of velocity at point I. What are I and J over here? I is the first trailer and J is the compound pendulum. Simple. I and J are two components. I and J depends upon what? I and J depends upon the numbers of degrees of freedom that we have. Okay, so we have like for a 2 cross 2 system, we'll have I varying from 1 and 2 and J varying from 1 and 2. For a 3 cross 3 system, I will vary from 1, 2, 3 and J will vary from 1, 2, 3. Okay, so this Mi comma J is nothing but the momentum associated with the point J for a unit change of or for the unit velocity at the point I. Clear? So we have 2 points only. One point is the trailer, which is going to have a velocity of x naught, and the second point is the compound pendulum, which is going to have a velocity, angular velocity of theta naught. Now the first case is going to be what? When x naught is 1 and theta dot is 0. X dot is 1 and theta dot is 0. So we have to find out Mij. So we know that our I is what? 1. I is 1 and J was what? J was the x and theta. So we have M11, M12. These are the two things that we have to find out. Okay. So x naught is 1 for a system. Initial velocity is 1. So what is going to be the momentum? First is M11, which is the moment associated with the trailer. Moment associated with the trailer. So for a mass, let us say M, some M random. If I give a velocity V, then its momentum is going to be M into V. So here M is going to be what? The total mass, M plus M into V, which is 1. Easy. For the second, what are we doing? Again, x dot is 1 only. There is no theta dot. But then M12 is what? It is the momentum which is associated with the second mass point. Moment associated with the second mass point. Now note over here, my first mass point was having a translation motion. So my momentum was a translation momentum, linear momentum. Okay. But my second point is actually a compound pendulum which is going through rotational motion, Now because of that rotational motion, it is going to have what? Angular momentum. It is not going to have linear momentum. So for angular momentum, what do we have to do? MRV, M into radius, or we can say the distance of the center, distance of the pivot point to the center of mass into V, which is the velocity that is given to the center of mass. So M, because my compound pendulum is having a mass M, then its center of mass is located at L by 2 and then the velocity 1. So these are my influence coefficients. For what? X not equal to 1. Okay. For the momentum of 1 given to the system. Second case is going to be what? Second is going to be theta dot is equals to 1 and x dot is going to be what? 0. X dot is going to be what? 0. Now for that case, what is happening? We are now giving theta dot as 1. Okay. So if theta dot is 1, now we have what? Now we have, you remember Mij, J was where our momentum was given and I was the points. So this time it is going to be M1, 2 and M2, 2 because the momentum is given at the second mass point and its effect is seen at 1 and 2. So M12 and M22. So for M12, what is going to happen? We don't have any, we don't have any kind of a uh, linear velocity or translation velocity input that is being given. Rather, it's an angular velocity. But the point 1, which is our trailer, it is what? It is translating. So we need to convert our angular velocity into what? Translational velocity and then multiply it with mass. Simple. So if my small mass m is given an initial velocity of theta dot, the velocity of the center of mass is going to be what? L by 2 into 1 and into the mass of the compound pendulum. So m into L by 2 into 1, right? Similarly, for M22, what do we have to find out? We have to find out that, okay, what is going to be the effect. Now, M22, my second point, mass point, which is a compound pendulum. First, it is able to rotate. Second, third, it is given an angular velocity. So, what is the effect of M22, which is the angular momentum? It is given as I theta dot, right? So m L square by 2 into 1, not 2, 3. Yeah, it is pivoted at the end. ml square by 3 into 1. So this will give us ml by 2, ml square by 3. Now with the help of this, now we can find out the mass matrix M11, M12, M21, M22, which is capital M plus small m, capital M plus small m, ml by 2, ml by 2, ml square by 3, ml square by 3. Okay. Now, if I compare it with when I found out the equation of motion, it is exactly the same. So I didn't have to get into finding out the equations, doing the force balance, and then finding out the equation of motion, then arranging it in this form, and then finding out what is matrix M, K, C like that. But over here, we just used the concept of inertia influence parameters, and then we found out the matrix M. Okay, I hope this was clear. Coming on to question number 2, wherein we have to find out the equation of motion of the 3 degree of freedom system and obtain the stiffness influence coefficients of the system shown below. Okay, so earlier we found out the inertia influence parameter. This time we have to find out the stiffness influence parameter. Okay, again we'll just find out the equation of motion, which is now easy for us, and then we'll compare it with how it is giving us similarity with the stiffness influence coefficients. So finding the equation of motion, we have to do nothing, but we have to write the force balance equations. So for mass m1, if it is getting displaced in the x1 direction, force over air is m1 x1 double dot. There is this k1 x1. Here we have k2 x1 minus x2, correct? Because of the relative displacement between m1 and m2. For mass m2, we have x2, we have m2 x2 double dot. Over here we have again k2 x2 minus x1, and over here we are going to have k3 x2 minus x3. Then we have m3 and x3. So we have m3 x3 double dot and a force k3 x3 minus x2. I hope this is clear. This is nothing but force balance method. We have just applied the method of force balance in order to find out that what are the forces that are acting on the system. Again, this K2 x1 minus x2 and the K2 x2 minus x1, it is because of the relative displacement. So what we are doing is we are basically finding out the relative displacement with respect to the mass, right? Like for K2, for M1, we have K2 x1 minus x2. So the displacement of x1 with respect to x2. And then for M2, we have K2 x2 minus x1, the displacement of x2 with respect to x1. And you can see that why there is this difference of this minus by equating the direction of the forces as well. Okay, I hope that is clear. Now, using this, we can now write the equation of motion. It is going to be m1 x1 double dot. This is k1 x1, then k2 x2. So plus k1 plus k2 x1 minus k2 x2 is equal to 0. m2 x2 double dot. Then we have k2 into x2 and k3 into x2. So plus k2 plus k3 x2 and then k2 into x1, k3 into x1. The minus k2 x1 minus k3 x3 is equal to 0. And then m3 x3 double dot plus k3 x3 minus k2 x2 is equal to 0. So this can be written as m x double dot k c x dot is equals to 0. So m is m1 0 0 0 m2 0 0 0 m3. Okay, and then we have k as k1 plus k2 minus k2 0 minus k2 k2 plus k3 minus k3 0 minus k3, sorry, it should be minus, just a second, it should be minus, yeah, k3 only, and k3, this one. So this is our stiffness matrix, correct? Now, this was the stiffness matrix that we got by using the equation of motion, but we can now use the concept of stiffness influence coefficients also over here. Okay. So again, what does the stiffness influence coefficient say? Earlier we were using the mass influence coefficient. Now we'll be using the stiffness influence coefficient. Just a second. Okay. So wait, let me just draw the diagram. M1, M2, M3. So if you remember for the inertia coefficients, we were talking about momentum. For stiffness, we will be talking about force. So the stiffness coefficient Kij is defined as the force. It is defined as the force which is acting at a point I. Yeah, which is acting, wait, yeah, which is acting at the point I. The force that is acting at the point I for a unit displacement, at the point J. Again, I and J are nothing but the mass points. So let us say that my one mass point, which is the first one, it is getting displaced by a unit value, which is x is equals to 1. Okay, then whatever force because of that is going to happen, or whatever force is required for that unit displacement to happen in the system at the mass point 1, mass point 2, and mass point 3 is defined by Kij. Okay, so what do? We just use the concept of force balance, nothing else. Nothing else needs to be done. Okay, so we'll just consider the three cases simply. First one is when this is M1, this is M2, and this is M3. So the first case is when what is happening? A unit displacement is happening for the point mass M1. So for the point mass M1. So M1 is getting displaced by x1 is equals to 1. Okay, now for that the force is going to be K11. For this the force is going to be K12, and for this the force is going to be K. Okay, it should not be 1 2, it should be 2 1 and 3 1. So for the point J, we have a unit displacement. Corresponding to that, we are going to have a contribution of forces on the point M1, M2, and M3, which is termed as K11, K21, and K31. So x1 is 1, x2 is 0, x3 is also 0. So basically only x1 is mass m1 is getting displaced by a unit force, by a unit distance, and m2 and m3 are going to be there only at that position. We assume so. Okay. Now because of this, what are the forces? First force is over here, which is K1, x1, which is going to be equal to K1 because x1 is 0. Over here, we are going to have forces K2, x2 minus x1. Now since x2 is 0, we are going to have it as minus K2. Over here, we are going to have K3, x3 minus x2, x3 and x2 both are 0. So this is going to be simply 0. Now, if I write the equation of motion, what is it going to be? See, over here we have three forces. Over here we have three forces, and we just have to equate the forces. Correct? So we have K11 minus K2, K11 minus K2 is equal to K1. Simple. Because K11 over here we considered as a force. The force which takes place, or the force that is required as mass M1, mass point N1 to cause a unit displacement as x1. Okay. So for unit displacement of J, whatever force is required at I. This is the first equation. Second equation is K21 is equal to minus K2, and K31 is going to be 0. These are the first set. So this gives us K11 as K1 plus K2, K21 as minus K2, and K31 0. These are the first set. For the second case, M1, M2, M3. We have a unit displacement x2 of 1, and x1 is going to be 0, x3 is also going to be 0, and forces are going to be what? Point J is going to be what? 2 over here, and point I is going to be 1, 2, and 3. K12, K22, K32. Okay. Now, if we come on to the force balance, here we have 0 because x1 is 0. Here we have this and this, which is k2 x2 minus x1. Now x1 is 0 and x2 is 1. So we have it as k2. And this we have what? K3. Okay, here I should write k3 x3 minus x2. So minus k3 because x3 is 0. So for this, when we write the equations, we have k12 is equals to minus k. Then we have k22 minus k3 is equals to k2, which implies k22 as k2 plus k3. And then we have k32 as minus of k3. These are the another three set of the values, and the last one is going to be m1, m2, m3. We have x1 as 0, x2 as 0, and x3 as 1. 0, 0, because x2 and x1 both are 0. Okay, maybe I should write this thing over here, k13, k23, k33. This is going to be k3 x3 minus x2, so k3. So what do we get? We get k13 as 0, k23 as minus k3, k33 as k3. These are the three set of last three set of values of the stiffness influence matrix. Now, what do we have to do? We just have to now put it together to find out the K matrix, nothing else. So K is going to be K11, K12, K13, K21, K22, K23, K31, K32, K33. Anyways, doesn't matter whether you write 2 1 over here or 1 2 over here, because as you know, the stiffness matrix is nothing but a symmetric matrix. We are going to get K1 plus K2 minus K2 minus K2, K2 plus K3 minus K3 minus K3, K3, 0, 0. Okay, I hope this is clear. And anyways, we got the same matrix from the equation of motion as well. Look over here, this one. We are getting the same matrix from the coefficient method as well. So it depends upon what do we require and what seems easier for us to find out the equation of motion. We can go through the generic method of finding out the equation of motion and then arranging it. But then if we have multi-degree of freedom systems, 8 or 9, then it is better to use these equations in order to get the equation of motion. Okay, now coming on to question number 3. I feel that this is a very interesting question. Okay, so we have to find out the stiffness matrix. Okay, first is we find the equation of motion. But as you can see over here, the point B has 3 degrees of freedom. Point B has 3 degrees of freedom, x, y, and theta, right? So it becomes difficult for us to actually work upon. See, for the earlier case, we had a simple strip spring mass dashboard system. But this is a complicated system, if we'll see, because the point B is free to move in the X and Y plane and along with that rotate with respect to that also. The Z axis, it is free to rotate. So it is a 3 degree of freedom system. We need to find out three equations and then we can arrange it and find out the stiffness matrix. But we'll prefer using the coefficient method, okay, influence coefficient method. So first thing that I would like to tell you, this you can read from a strength of material book. I'm just giving you the final equations because that would take a lot of time if I start deriving it. So you can just get through it from the strength of material book. Okay, so see, for any beam, for any beam which is fixed at a point like this, it is free. It is free from one end. Okay, it is free from one end. It is free from one end. We have something like this. We have three cases. Okay. Firstly, we can write this beam something like this, where there are these 2 points. Okay. And let us say that it has E, I, and L. Okay. Parameters. And there are two forces, F2, F1, and F2. Okay. Apart from that, it is going to have theta 2, theta 1. And then there is going to be the displacement in the above direction, which is going to be W1, W2. Okay, the deflection of the beam at the 2 points. Though for the fixed support, it is going to be 0, but we are just saying that okay, for now we are considering. Now there are two cases that can happen. First case is when W1, first case is when W1 is going to have a value and theta 1 is going to be 0, which means that the beam is getting deflected in such a way such that it is straight. It is not having any angle with respect to the point. So it is something like this. Something like this. So we have this as W1 and theta 1 is 0 over here. Okay, then what are the forces? The force values are given as there's going to be forces and then moments. So I'll just write it. We have F1 as 12 EI W1 by L cube. F2 as minus 12 EI W1 by L cube. And then there are moments which may be written as 6 EI W1 by L square, 6 EI W1 by L square. Okay. Another case could be when the deflection is 0 and then your angle is not 0. Something like this. W1 is 0, but then we have a theta. Okay, in this case again F1 is going to have a value of 6ei theta 1 by L square. F2 is going to be minus of 6ei theta 1 by L square. M1 is going to be 4ei theta 1 by L. M2 is going to be 2ei theta 1 by L. Okay, so this is known to us. Now we have to just apply it for our system. See, we have three directions, so we have to consider three unit displacements. One as x is equals to 1, another as y is equals to 1, and the third one as theta is equals to 1. Okay, so for the first case, when we consider, deflection along x with x is equals to 1. So how is the system going to behave? If my initial system is something like this, it is going to deform only in the x direction. So this beam is now going to be this is now going to be like this, where this is 1. Okay, and we have A, B, C, A, B, C. This is the point B. So if you look closely, for point A, we do not have any deflection nor do we have any change of theta. It is happening only for the part BC. So we need to calculate the moment and forces for the point BC, definitely. Because what do? We calculate the contribution of forces for the unit displacement in one direction. So for that unit displacement, we have x and we have to contribute its we have to find out its contribution in the x, y, and theta direction. Okay. So firstly is in the x direction. In the x direction, what are we going to have? We are going to have a force. We are going to have a force which is given over here. This one, which is 12 eiw1 by L cube. F of x 12 ei by w1 is 1 L cube. This is for BC. Now if you look over here for BC, we have 2L. The length is twice. So in the denominator we are going to have 8 and then we can cancel out the terms. So effectively it is going to be 3 ei by twice of L cube. Okay, this is the force contribution for in the x direction. Now coming on to y, what is it going to be? For the y, we do not have any lateral displacement, nor do we have any angular displacement. So this is going to be 0. And for moment about theta, what do we have? Look over here. For moment about theta, we have a moment over here which is 6 eiw1 by L square. So 6 eiw1 by L square. This is again for BC. For BC, L is twice of L. So 4. This is going to be 3 ei by twice of L square. This was for the first case. Second case, deflection along y with y is equals to 1. So what is happening in this case? Okay, this is y, and then this is 1. Earlier, for we were concentrating on the BC element, now we'll be concentrating on the AB element. Simple. So again, f of x is going to be 12 EI by L cube, but this time it is for AB, and for AB I think we have different values. Yes, L is the same, only I is twice. So 24. 24 EI by L cube. The force is definitely acting in the positive y direction. This should be f of y. F of x is actually 0. And then we have m of theta, which is c. It is important to note over here the direction of m1, right? So m1 is essentially in this direction, outside. So over here, if you look, we had m1 like this, but over here we have it like this. So essentially, we have already considered the anti-clockwise direction as positive. So definitely here we'll have the same equation but with a minus 6ei by L square. This time for AB, it is going to be minus of 12 because I is twice. 12 EI by L square. Okay, I hope this is clear. The last part is angular deflection. Theta is equals to 1. Theta is equals to 1 this time. Okay, so theta is equals to 1. So it is something like this. The displacement is 0, but then there is a angle theta, right? So we'll have fx, fy, and then what was the angle? Sorry, what was the direction of movement? So direction of movement is going to be again in the outward direction, something like this. Something like this. Okay, I hope this is clear. Now, if we look into the second part, because see, we do not have a deflection over here, but then there is this angular movement. The second one can also have angular movement because we have theta is equals to 0, which is the angular movement at B as, sorry, theta is 1, angular movement at B, right? So because of that, the first part is also going to have some contribution, okay? Now in this case, fx is going to be what? We know it from here. Fx is going to be 6ei theta 1 by L square. Theta 1 is 1, so 6ei by L square, which is for x direction. This component is not going to have any effect, rather this component is going to have. Okay, so for BC, you're going to have 3ei by 2L square. F of y is going to be because of this component, right? 6ei by L square AB twice 12ei by L square. Okay, and then this is going to be with a minus, right? This is going to be with a minus. Definitely it is going to be with a minus. M of theta is going to have contribution of both of them. Contribution of both of them. So it is going to be 4, I guess it was something like 4ei theta 1 by L. 4ei by L for BC. 4ei by L for AB. For BC, we have twice of L, 2ei by L plus 8ei by L. It's going to be 10ei by L. Okay, I hope this is clear. Okay, now if we write the equation, it is going to be something of F is equals to K into X. F of X, F of Y, M. And then we have X vector as X, Y, theta. So K is going to be nothing but EI by L cube 3 by 2, 0, 3L by 2, 0, 24 minus 2L, 3L by 2 minus 2L, 10 L square. This is going to be this is actually the stiffness coefficients. I hope this is clear. Okay, I hope this is clear. Anyways, if you look over here, we have a minus over here and then we have a plus over here. That is because with this kind of displacement, this is also going to have some displacement like this. Okay, so because of that only, if you look at the force in the direction of y, it will come in the negative direction, and the moment is also going to come in the anti-clockwise direction, so it is going to add up. Okay, coming on to question number 4. We have to determine the flexibility influence coefficients. See, earlier we found out the stiffness influence coefficient. Flexibility influence coefficient is nothing but the inverse of the stiffness influence coefficient. Basically, Aij gives the deflection at point 1 due to load at point J, or we can write it like this. Yeah. So if a load of unit amount is applied at point J, what is going to be the deflection at point 1, 2, and 3? That is what we get from that is what is the influence coefficient. If you remember stiffness case, we were actually relating the deflection. We were actually giving a unit deflection and then we were finding out the force. Over here, we are talking about a point load, and then we are actually looking on to what is the effect on deflection. Okay, so Xij is aij into fj. Basically, a vector into f, sorry, a is not a vector. A into f vector is going to be a k f, correct? Because we can write, okay, should not be f, this should actually be x. X, because f is nothing but kx. F is nothing but k into x, correct? So that is what we have done over here. In that case, a into k is I. I is the identity matrix. So A is the inverse of k. That is what I was saying. Flexibility influence coefficients is nothing but the inverse of the stiffness coefficient. So now if I want to find out, I'll just do it quickly. For mass m1, m2, m3, we have given our unit force F20, F30. Okay. So what are its effect? We know F, the relation between F and this A. What is it? It is nothing but see, look over here. From here we can see, right? From here we can see. A is what? Deflection, right? So deflection can be multiplied with K in order to get the force. Deflection can be multiplied with K in order to get the force. Okay, I hope this is clear because we have Kx is equals to F, right? But then our F is 1. Our F is 1 and A is nothing but 1 by K, right? So using that, we can just write the forces that are acting like K1, A11, A11. What was A11? A11 was the deflection of mass point 1 for a force 1 applied on mass. So X1 is going to be A11. Then here and here we are going to have K2, A21 minus A11. Here K3, A31 minus A21. Now if we write K1 A11 is equal to K2 A21 minus A11 plus 1. Then for the second one we are going to have K2 A2 minus A11 is going to be equal to K3 A31 minus A21, right? And then K3 A31 minus A21 is going to be equal to 0. These are the first set. For the second one, we're going to have M1, M2, M3. Then we have a force F2 as 1, F3 as 0, F1 as 0. Talking about the forces, K1, A11, K2, A21 minus A11, K3, A31 minus A21, equating A11, K1 is equal to K2, A21 minus A11, K2, A21 minus A11 is equal to K3, A31 minus A21 plus 1, and then definitely K3, A32 minus A22 is equals to, okay, here it should not be 1 actually. It should be rather, now the force is at point 2. Definitely it is going to be 1, 2. It is going to be 1, 2. So 2, 2, 1, 2, 3, 2, 2, 2. 1, 2, 2, 2, 1, 2, 2, 2, 1, 2, 3, 2, 2, 2. Okay, and for this third case, the forces are definitely going to be the same. Only the thing is that now 1 is going to be there in the third equation. Okay, so finally it's going to be something like K1, A13, K2, A23 minus A13, K3, A33 minus A23. This will give us K1, A13, K2, A23 minus A13, K2, A23 minus A13 is equals to K3, A33 minus A23, and K3, A33 minus A23 is equals to 1. Is equals to 1. So these are the equations. Now if you are going to solve these equations, these are linear equations, you can just solve it. You are going to get the relations something like K A11 is equals to A21 is equals to A31 as 1 by K1. Then you are going to get A12 as 1 by K1, A22 as 1 by K1 plus 1 by K2, and A32 as 1 by K1 plus 1 by K2, A13 as 1 by K1, A23 as 1 by K1 plus 1 by K2, and A33 as 1 by K1 plus 1 by K2 plus 1 by K. Then you can just arrange it in order to get the flexibility influence coefficients. I hope that this is clear now. Coming on to question number 5. Now we have to find out the flexibility matrix for the beam shown over here. Here we don't have to find out the stiffness matrix, but rather we have to find out the flexibility matrix. Again, what was the flexibility matrix? Flexibility was nothing but the inverse of the stiffness. Inverse of the stiffness matrix, right? And that is what we have to find out over here. So now look over here. We have a simply supported beam. We have a simply supported beam. Just a second. So we have a simply supported beam, and then the beam is considered massless. This is massless. And we have three masses at a distance of L by 4, L by 4, and L by 4. Okay. So what was the idea of Aij, which is the flexibility influence coefficients? The concept was simple that a load, if a load is applied, if a load is applied at point J, if a load is applied at point J, so if a load is applied at point J, right? If a load is applied at point J, then what is going to be the deflection at point I? What is going to be the deflection at point I? It's very simple. And a load is going to be the load that I'm going to consider at point J. It is going to be the unit load. It is going to be the unit load. So if a unit load is applied at point J, the deflection at point I actually gives us the flexibility influence coefficient at that point. For this case, what we can do is we can convert it into three cases because we have three masses, three mass points. So our J is going to be 3. For the first case, we are going to have a mass, not mass actually, load of 1 unit that is applied at the point of mass 1, which is M1. Okay. And then because of that, the deflection at the 3 points, because of that unit mass is going to give us the flexibility matrix values. It's very simple. That is what we did over here also, right? That is what we did over here also. Okay. So for this, again, we have a beam. So for a beam, we have something like this, which bends like this. We have this, this, and this. If the load is over here, 1 unit load, then these deflections are known as A11, A21, A31. Simple. And then what are its values? So I'm not getting into how to evaluate it, but for a simply supported beam, how we are going to calculate the deflections at these 3 points, you can find it in any of the sense of material book. Since it's a point load, this is the easiest one. So A11 is going to be 9 L cube by 768 EI. A21 is going to be 11 L cube by 768 EI. And A31 is going to be 7 L cube by 768 EI. Similarly, these cases can happen, and then the point load can be at this point or this point. A21, A22, A, okay. Now the load is applied at point 2, A12, A22, A32, and then here we are going to have A13, A23, A33. So by using the idea of strength of materials, we are going to get A12 as A21, which is going to be 11L cubed by 768 EI, A22 as L cubed by 48 EI, and A23 as 11L cubed by 768 EI. Again, A31 as 7L cubed by 768 EI, A32 as 11L cubed by 768 EI, and A33 as 9L cubed by 768 EI. So this is what we are going to get. So by using these, we can simply write A as nothing but L cubed by 768 EI into 9, 11, 7, 11, 16, 11, 7, 11, 9. This is going to be the flexibility influence coefficient matrix. Okay, so determine the eigenvalues and eigenvector of the matrix given below. Okay, I forgot to add the matrix. Anyways, use the same concept to find the modal frequencies and mode shapes of the 3 degree of freedom system of question number 2. Okay, firstly, the matrix that I had to include was 4, 3, 2, 0, 0, 0, 0, 1, 0. I've taken a simple matrix basically because I have to give you the concept of how we are using this to find out the modal frequencies and mode shapes. Anyways, so for this matrix, if I have to find out the eigenvalues and eigenvectors, what do I do? So for the eigenvalue, we do nothing but A minus lambda I. We find the determinant and make it equal to 0, right? So 4 minus lambda 1, 0, 0, 3 minus lambda 0, 0, 0, 2 minus lambda. Determinant of this is equal to 0. This is going to give us 4 minus lambda, 3 minus lambda, 2 minus lambda is equal to 0. So lambda is going to be 2, 3 and 4. 2, 3 and 4. We are going to get these three values of lambda, which are the eigenvalues. Now corresponding to these eigenvalues, I have to find out the eigenvector. See, in order to find out the eigenvectors actually satisfy 4 minus, not 4, A minus lambda I into x is equal to 0. This is what the eigenvectors satisfy. So if I find out A minus lambda I, then I can just find out the values of x. Since I have three eigenvalues, so I'm going to have three eigenvectors. So the eigenvector for the first eigenvalue, which is lambda is equals to 4. What do we have? A minus 4i. That is going to give us 0, 1, 0, 0, minus 1, 0, minus 2. 0, 1, 0, 0, minus 1, 0, 0, 0, minus 2 into x, y, z, 1, 1, 1 is equal to 0, 0, 0. So multiplying it with the matrix A minus 4i, and then we try to find out, we get y of 1, 0 and z of 1, 0. For x, we do not have any condition, which means that x is a free vector. So we can consider x as 1. So the first set of eigenvalue is 1, 0, 0. Second set, for lambda 3, we have 4 minus 3 is 1, 1, 0, 0, 0, 0, 0, 0, minus 1. Zero, zero, zero. Okay. Okay, this is not x square, it is x2. Okay. Now maybe I should write it like this, it will be clearer. Okay. So what are the equations that we get? First is z of 2 is 0. Second is x of 2 and y of 2 is equal to 0. So y of 2 is minus of x of 2. Z is going to be 0, and whatever is going to be the value of x, y is going to have a value negative of it. So x of 2 is 1 minus 1, 0. Third case is for lambda is equals to 2. We're going to get 2, 1, 0, 0, 1, 0, 0, 0, 0. Okay. So the first thing is y of 3 is 0. And since y of 3 is 0, we have twice of x of 3 plus y of 3 as 0. So if y of 3 is 0, x of 3 is also going to be equal to 0. And thus, only z of 3 can have any value. So x3 is going to be, so these are the three eigenvalues and the eigenvectors. Now we have to use the same concept for the 3 degree of freedom system, which was considered in question number 2 over here. Okay, and we have to find out the eigenvalues and the eigenvectors. Fine. See, it is important to understand over here that for these kind of a systems, for a 3 degree of freedom system, the eigenvalues and eigenvectors are essentially associated with the modal frequencies and the modal shapes, which means that basically the eigen values are nothing but the natural frequencies of the system that you can solve also on your own to understand. So when we are using the matrix which we obtain for a 2 degree of freedom or 3 degree of freedom system, and we find out its eigenvalues, it is essentially the modal frequencies, and eigenvectors are nothing but the model mode shapes. Okay, and why we are concerned about it? Because during those frequencies, if my system is vibrating at those modal frequencies, what is happening is that all three systems are oscillating at a single frequency. None of them is also having the component of the other frequency. Like for example, for 3 degree of freedom system, we have three masses, so it should have three frequencies. But when it is oscillating at one of the modal frequency, only one frequency is having the contribution. The other two does not have any kind of a contribution, which means I can write the solution in terms of only one frequency. But if I want to write out the general solution, it will be amalgamation of the three frequencies. Okay. So that is why we try to find out the modal frequencies and the mode shapes, so that if we know three independent solutions, independent because they are not dependent on the other two frequencies, we get the three independent solutions. We can just write the closed form solution for any general case as the linear combination of the three parts. Okay. So we'll just add a slide and just consider that K1, K2 and K3 are equal to K, and M1, M2, M3 is equal to M. These are the two assumptions that we are considering. Okay. So we define a dynamical matrix D as K inverse of M. K inverse is what? A matrix. K inverse, if you'll find out, it is going to be 1 by K, 1, 1, 1, 1, 2, 2, 1, 2, 3. Anyways, the K matrix is nothing but K minus K, 2K, K, 2K, minus K, minus K, 2K, 0, 0, K, K. This one. Okay, this is K inverse. And D is nothing but K inverse into M. When we'll do the matrix multiplication, we are going to get it as 1, 1, 1, 2, 2, 1, 2, 3, because M matrix is nothing but M multiplied with an identity matrix. So any matrix multiplied with the identity matrix is going to give us the matrix itself. Now we find out the determinant that we have to make equal to 0, which is nothing but lambda of identity matrix minus D matrix. This is going to be 0 minus M by K 1, 1, 1, 1, 2, 2, 1, 2, 3 is equal to 0. Lambda is nothing but 1 by omega square. So now if we solve it, we can just, for now, we can assume, see over here we are going to have lambda minus M by K. Okay, lambda minus M by K. If I divide everything by lambda, we get M by K into lambda. So we can just assume alpha as M by K into lambda. So then get the equation as 1 minus alpha minus alpha minus alpha minus alpha 1 minus 2 alpha minus 2 alpha minus alpha minus 2 alpha 1 minus 3 alpha. This is going to be equal to 0. Okay, I hope this is clear. So now when we try to solve it, what do we get? We get alpha 1 as M1 omega 1 square by k, which is 0.19806. I've already done the calculation. Since this is a uh, polynomial with a degree of 3, it will take a time to solve. We'll need to see how to solve it. So I've just solved it using MATLAB and I'm giving you the solution. You can solve it using MATLAB or you can solve it manually also. Like we assume one of the roots and then we try to find out the other roots by dividing or by actually dividing the this characteristic equation with whatever the root is, like alpha minus, let us say the first root is lambda 1, so alpha minus, not lambda 1, alpha 1, alpha minus alpha 1, then divided by that, and then we get a quadratic equation, and then we find out the roots by the quadratic equation likewise. Okay, so for this, so this implies omega 1 is nothing but 0.44504 under root k by m. Then we have alpha 2 as m omega 2 square by k, because m1, m2 and m3 are all equal, is equal to 1.5553. This implies omega 2 as 2471 under root of k by m. Then we have alpha 3 as m omega 3 square by k, 3.2490, which implies omega 3 as 1.8023, 5 I guess, under root of k by m. So these are the three frequencies which are essentially the modal frequencies, and using these now we can find out the mode shapes. How? Let us see that. So first mode, we have omega 1 as 0.44504 under root k by m. Lambda 1 corresponding to this is going to be 5.0489 m by k. So if we put it again, if you remember, like in the previous question, what we did, we used a minus lambda I into x is equal to 0 because that is what eigenvalues satisfy, and eigenvalues are nothing but the mode shapes. Likewise, we are going to do it over here also. What we did was we wrote lambda I minus r d is equal to 0 determinant. So lambda I minus d into x is going to be 0. And so taking lambda 1, we are going to get 5.0489 m by k 100,010,001 minus m by k 111,122,123 x1, x2, x3. This is for the first 111. This is equal to 000. Solving this, we are going to get the values. So I'm going to write the final value only. Get x of 1 as 1 of 1, 1, 1.8019, 2.2470. This is the first mode, which means for x1 value of displacement in the first, for the first mass, if the displacement is x1, then for the other two it is going to be a multiplication with the x1 with these two values that we are getting. Okay, so these are going to give us the mode shapes, which means that when it is oscillating, a first system is oscillating at the first mode, which is omega 1, all the three masses are going to follow the same direction. Okay, all the three are going to be having the same direction, and first mass is going to have whatever the displacement is, the second one is going to have more than that, and the third one is going to have more than the second also. So it is going to be the sum, going to be something like this. Right. Something like this. This is x1 of 1, x2 of 1, x3 of 1. This is the first mode shape. At the first modal frequency, they are going to have such kind of a oscillation arrangement. For the second mode shape, we have omega 2, 1.2471 under root of k by m. Lambda 2 is 0.6430 m by k. Okay, putting this 0.12 1, 2, 2, 1, 2, 3. X1 of 2, x2 of 2, x3 of 2. 0, 0, 0. This is again going to give us the mode shape as like this and this. X1 of 2, x2 of 2, x3 of 2. This is the third mode shape, which means for a displacement of x1, okay, this should be multiplied with x1 of 2 actually, and this should be x2. This, yeah. So for a displacement of x1 of 2 for the mass m1, the second mass is going to have a fraction of its displacement in the same direction, and the third mass is going to have around 80% of the amplitude of displacement, but in the negative direction of where x1 is going. So first two masses are going to be in the same direction, and the third mass is going to be in the negative direction of the first two. This is the second mode shape. And the third mode shape, third mode shape, which is corresponding to omega 3 as 1.8025 under root of k by m, and the corresponding lambda 3 is 0.3078 m by k. We get 78 m by k 100,010,001 minus m by k 111,122,123. x1 of 3, x2 of 3, x3 of 3 equal to 0, 0, 0. This will give us x of 3, the third mode shape, as x1 of 3 into 1 minus 1.2468 0.5544. So now if I try to plot it, so this is the mode shape, the third mode shape corresponding to the third modal frequency or the third natural frequency, in which we can see that if the first mass is getting displaced by an amount x1 of 3, the second mass is going to get displaced by around more than 20% of amount extra, but in the negative direction. And then the third mass is going to have around 50 to 55% of the amplitude of the displacement of the first mass. Okay, so in this case, the first and the third mass are going to be in the same direction, while the second one is going to be in the negative direction for this. Now, this is for the third mode shape. So, as we saw that for a 3 degree of freedom system, where we had to find out the modal frequencies and the mode shapes, what did we do? We used the concept of eigenvectors and eigenvalues. As I've explained it earlier also, that for any three-dimensional system, if we get three independent solutions, we can just write the general solution as a linear combination of these three independent solutions. And these three independent solutions we are going to get on the basis of the knowledge of the three mode shapes and the three modal frequencies. Because when the system is oscillating with any of the modal frequency, all the three masses are going to have the same frequency, and then we can write the solution in terms of only the that particular frequency and mode shape. Okay, I hope this was clear. So I think we are already done with the time. Yeah, so thank you so much for today's live session, and we have completed the 9 week live sessions for this course. So yeah, I hope these questions will be helpful for you to solve the assignment problems. And I think I've mentioned the date wrong over here. It should be 23. Sorry for that. So thank you so much, and we'll meet next week for the 10th week live session. Now I'll end the meeting. Thank you.